In this video, we're picking up again in section 6.3. In the first video, we talked about the Taylor and Maclaurin series and went over some examples of how to find a Maclaurin series. Now, in this video, we're going to talk about the Taylor series. And the only real difference is, remember, the Maclaurin series, we're going to center our power series at x equals 0, whereas the Taylor series can be centered anywhere. And so if you see in example 3 here, it says find the Taylor series for the function 1 over x squared about x equals -1. So we have a different center. It's now x equals -1. And then we're going to find the radius of convergence, just like the last one. And so we're going to start off in the same way. We're going to put the table here to show our derivatives. And so let's go down through again the first 5 terms. So 1, 2, 3, 4. And then we're also going to attempt to find an nth term. So again, we have our function and its derivatives. So our original function is 1 over x squared. And so it would be nice, though, if I kind of think about this as a power, right? So if we think of it as a power, we're going to take that power to the front, which is going to give us a -2. And then we're going to subtract 1 from the power, which is going to make it -3. So it's going to become 1 over x cubed. And we can continue that on. Again, if we think of our power as -3, and we would multiply that -3 to the front, so we'd have -2 times -3, which is going to be +6. But rather than multiply it out, just so we can see some sort of pattern, I always recommend that you just leave it. So this is going to be -2. The new derivative you're going to multiply by -3, and now it's going to become 1 over x to the 4th, right? And then we just continue this pattern. So next one, we're going to have -2 times -3 times -4 times 1 over x to the 5th. And then one more here, -2 times -3 times -4 times -5 times 1 over x to the 6th. And that pattern continues. Now, let's go ahead and plug in, let's evaluate that at the center value. So in this case, the center is -1, so we want to find f and its derivatives at -1, which really is just going to, the only place it's going to be plugged into is in the denominator, right? So we have that in the first one, we have 1 over x squared. That's just going to be 1 over 1, right? Which is 1. And then when we plug in -1 to the next one, we have -2 over -1 cubed. So that's actually 4 negatives. It's still going to be positive, but we're going to have a +2. All right, and we plug in again. 1 over x, -1 to the 4th is +1, and -2 times -3 is +6. But we can think of this as 2 times 3, right? Are you seeing a pattern here? Looks like we're coming up on some sort of pattern. Let's go again. Again, we're going to have 2 times 3 times 4. Okay, and then the last one, and it's going to be positive, right? All these are positive. And the last one is 2 times 3 times 4 times 5. These are all factorials. This is 5 factorial. This is 4 factorial. And 3 factorial, and 2 factorial, and 1 factorial. So what you'll notice is that for n equals 0, we have 1 factorial. So the number there is 1 bigger than 0. 2 factorial for 1, so 2 factorial, but n is 1. 3 factorial, but n is 2. In every case, you take n and you add 1 to it to get the factorial. And that's our formula. So that tells us that in order to get our function is 1 over x squared, we have a power series that's going to go from 0 to infinity, and it's going to be f of n, or the function and its derivatives, right, over n factorial times x minus a, but in this case that's -1, so it's x plus 1 to the n. Now, the thing is this part right here, let me circle it, this part right here, we just found the formula for that. That formula is right there. And so our answer here is we're going to get the sum, n equals 0 to infinity, of n plus 1 factorial over n factorial. And we've seen over and over again how to simplify something like that. That's something we did in Chapter 5 when we did the ratio test. We know that n plus 1 factorial over n factorial is just n plus 1. And so this is basically n plus 1 times x plus 1 to the n. And that's our Taylor series. Okay, now we do need to find the radius of convergence. So rho is equal to the limit as n approaches infinity of n plus 1 or n plus 2 times x plus 1 to the n plus 1 over n plus 1 times x plus 1 to the n. And that's equal to the limit of n plus 2 times x plus 1 over n plus 1. So we can pull out the x plus 1, which leaves the limit of n plus 2 over n plus 1. And of course that limit approaches 1, right? We know that that approaches 1. So if that limit approaches 1, that means what we are left with is the absolute value of x plus 1. And in order for that to converge, it has to be less than 1. And so we could rewrite it as an inequality without the absolute value, but we know right there that this is going to be r equals 1. That's the radius of convergence. So if our radius of convergence is 1, and our center is at -1, then that means that 1 unit to the right of -1 is 0, and 1 unit to the left of -1 is -2. So our interval of convergence is going to go from -2 to 0. Now let's visualize this. So if you look here at Desmos at x equals -2 and also x equals 0, you can see the blue curve that's increasing between -2 and 0. And you can see the red curve, which is our, that's our Taylor series. But right now, and you can, okay, and so the center of the Taylor series is listed over here. It's b equals -1. And right now, though, we just have the first term in that series. Now, if we slide a here, it is going to increase the number of terms. That's the first 2 terms. And as we keep going, now watch this red curve. Watch it kind of bend and go to the shape of 1 over x squared. It's going to get closer and closer. I'm going to slide again. It's looking better. I'm going to slide again. It's looking better. We're now at n equals 4. And as you keep going, look at that. Right there. Look, it's really pretty good, but notice as soon as you get outside of -2 or 0, it doesn't match anymore. It only matches between -2 and 0, and that was because the radius of convergence was what? The radius of convergence was equal to 1, and it had a center at -1. So And that's only with a few terms, but you can see that as you get outside of -2, this is the red curve no longer matches the blue curve. And as you get outside of 0, it doesn't match. So that's what we mean when we talk about radius of convergence and interval of convergence. Let's do one more of these. I think it'll be helpful to see another one because these are so new and so different. So let's look at example 4, and we have the Taylor series. F of x is the natural log of x centered at x equals 2. So we'll do the same thing. And I want you to go ahead and pause the video and do this next part on your own. I want you to make your table with the different values of n, find the derivatives, and then you can go ahead and see if you can come up with a formula for the nth term, right? So we have the nth term down here. See if you can come up with a formula for the nth term. All right, pause the video. All right, so hopefully you were able to get to this point. You may not have been able to come up with a formula for the nth derivative of f evaluated at 2, but hopefully you're able to write this pattern. Notice again, I didn't, just like with the last problem, I didn't multiply -1 times -2 and say that was equal to 2. I left it, but I did say, okay, well that's a negative times a negative, that's going to be a positive. And then like for n equals 4, there were 3 negatives on the top, so I made the whole thing negative. But I still left it as 1 times 2 times 3. So we can see that the sign is alternating back and forth. The easy thing about this one is we should be able to tell the denominator, right? The denominator is going to be 2. Notice the power on 2 aligns with the value of n over here. So if we're looking at this guy, that's n equals 4. So the power is going to be 2 to the n. But now, the other part, the numerator, 1 times 2 times 3, that appears to be following that factorial format. However, it's one smaller than n. So that's going to be not n factorial, but n minus 1 factorial. And then the only thing left is it looks like for odd terms it's positive, and for even terms it is negative, right? So we're going to have to do one of those -1 to a power things, but in this case we have -1, oops. In this case we have -1 raised to the n minus 1. That'll give you the right sign for each of those terms. Notice when n equals 1 we get a positive, when n equals 2 we get a negative, and so on. So sometimes you just have to kind of play around with those to see if it works out. I'm going to go ahead and rewrite this now. Okay, so here's the thing. These terms, n equals 1 to n, seem to all match this formula except for ln2. So it is all right. Sometimes we just peel off like the first term or the first 2 terms because it just doesn't fit with our power series. So for example, we could say that if our function is the natural log of x, we could say that this is equal to the natural log of 2, but then we can add a series that goes from 1 to infinity. And then our nth derivative evaluated at 2 follows the formula that we wrote. So we have -1 to the n minus 1 times n minus 1 factorial over 2 to the n, and then we have over n factorial times x minus 2 to the n. And what do we get? Just a reminder, looking at this denominator, working with factorials, I know we've done a lot of this, but n factorial is the same as n times n minus 1 factorial, right? So that means that when we go to simplify this, this is the same as the natural log of 2 plus we're going to end up with -1 to the n minus 1 times n minus 1 factorial over 2 to the n over n times n minus 1 factorial. And those n minus 1 factorials will cancel. And so let's write this one more time. This is the natural log of 2. Our series is going to look like negative 1 to the n minus 1 over 2 to the n times n. And then we have our x minus 2 to the n. And that's our Taylor series. Okay, so when we do need to find the radius of convergence again. So our rho is equal to the limit. And because it has absolute value, we can go ahead and ignore the negative 1 to the n minus 1 power, right? So we have x minus 2 to the n plus 1 over 2 to the n plus 1 times n plus 1 times 2 to the n times n over x minus 2 to the n. And then let's simplify. So we end up with x minus 2 over 2, we have n, and we have n plus 1. And I would say we could go ahead and pull out the x minus 2 and pull out the 1 over 2, right? Because we have a 2 in the denominator. So we have basically 1/2 times the absolute value of x minus 2 times the limit of n over n plus 1. And of course we know that that limit approaches what? That limit approaches 1. And so we end up with 1/2 times the absolute value of x minus 2. And that converges if it's less than 1, which means the absolute value of x minus 2 must be what? Absolute value of x minus 2 must be less than 2, which means r equals 2. So our radius of convergence is 2. Since our center is at 2, this interval is going to be, the interval of convergence is going to go from 2 to 4. And just for kicks, let's see what that looks like again in Desmos. So we have our ln function. Notice I put my center over here. B value is 2. And remember, our interval is going to go from 0 to 4. So as I slide this A, you should see that red curve starting to look like the blue curve, but it won't look like it outside of 4 or 0. So look at this. It's starting to match pretty good. But as soon as you get to 4 and 0, it starts to diverge, right? So it only converges between 0 and 4. And that's it. That's power series. So thank you.